Hello, Math 201. Today we're going to talk about section 3.8, implicit differentiation. I will say that this section is probably one of the harder sections that we'll have covered so far. And the homework especially is pretty difficult. There's only 10 questions, but there's just some kind of difficult algebra on it. So I just wanted to warn you ahead of time. And just know that, yeah, I'll be available and I can post some videos to help maybe with some of the problems later. But yeah, so let's get into it. Implicit differentiation. The idea of implicit differentiation is so in order to understand implicit differentiation, we should talk about what the opposite is, which is explicit. And so let's get into that. So the idea is that we have y equals some function of x. Then we say y is an explicit function in terms of x. Explicit being because when you plug in x, I know exactly what y is. It's you plug in some value here, and then that's the function y. But not all functions we deal with are explicit. So for instance, this is a function, right? You can plug in values of x and it'll give you values of y. And the points x and y that satisfy this equation are a unit circle, right? And in this case, y is an implicit function of x because it's not explicit how you find y if I give you an x value. You have to solve for y, right? The equation above implies that y is a function of x. So the implicitness means that it implies it's a function. We can solve for y to get an explicit function, right? So what you do is you subtract x squared from both sides and take the square root. And so y could be plus or minus the square root of 1 minus x squared. These are two explicit functions of x. And, we could take the derivative to find the slope. So for instance, this is the total equation. The top one is when y equals the square root of 1 minus x squared. And the bottom one is negative square root of 1 minus x squared. And we can find, the tangent line at points on these curves. And the idea is that the slope of the tangent line is still dy dx, right? The slope is still dy dx, right? The change in y over the change in x is the derivative. And at any given point, that's still true. Dy dx will still tell us the slope. So we could find dy dx by finding an explicit function and taking the derivative with respect to x. But what about if we're in an implicit form? Is there a way to take the derivative and find dy dx over here? And the answer is yes. So doing it the old way, chain rule tells us that y prime is 2x over the square root of 1 minus x squared, or negative 2x over the square root of 1 minus x squared, if you actually do the derivative of that function and that function. But what if we had an implicit function where we couldn't solve for y? Could we still find dy dx? And the answer is yes. And the way we do it is by using chain rule. So this is huge. We're using chain rule and the fact that d dx, the derivative with respect to x of y, is dy dx or y prime. Dy dx and y prime are interchangeable. And so here's the idea. Let's start with this function right here. We have x plus y cubed plus 2 equals 0. This is an implicit function of x, right? Y is an implicit function of x, but we could still find dy dx, which would still tell us the slope at any point for this curve or this equation. Step one, let's take the derivative with respect to x of both sides, right? Remember when I said that if you have an equality, if two things are equal, then taking the derivative with respect to x of both sides, they're still equal. And so let's do that. If you take the derivative with respect to x of both sides, the derivative of x is just 1. The derivative of 2 is 0. The derivative of 0 is 0. Now to take the derivative of this, how do we take the derivative of y cubed? Well, what if we let u be y, then u prime is y prime, and then the outside function is u cubed, and f prime of u is 3u squared. And so what we do is you take the derivative of the outside function, which is u cubed, and that's 3u squared, 3, and then you plug in y, and then you multiply by d dx of y, right? We take the derivative of the inside function, but d dx of y is just dy dx, and so we get 1 plus 3y squared times dy dx and equals 0. So take the derivative of both sides with respect to x, and then we treat y. We can treat it just like an x, right? This is what it would be if we just treat it like an x, but then you just need to remember to multiply by the dy dx. Then the final step is we want to solve for dy dx. And the way we do that is just some simple algebra, right? We can just solve for dy dx, subtract 1 over, then divide by y squared. So you get dy dx is -1 over 3y squared. And it turns out, we could have done that like this by solving for y and then taking the derivative, but that would have been actually more work. It's much easier to just do it doing the implicit differentiation to get dy dx, at least in terms of y. If we wanted in terms of x, we would need to do something a little bit more. But if we know what the y values are, we could still find what the slope is at a given point. And so here's the main idea. Implicit differentiation. If y is an implicit function of x, you can take the derivative with respect to x of both sides using chain rule for expressions with y. So whenever you have y, just take the derivative as though it's x, so that's where the 3y squared is, and then just multiply by dy dx. And then the final step, or step 2, is to solve for dy dx. And dy dx in general will be an expression that involves both x and y. And so let's do another example. So here's our circle example, x squared plus y squared equals 1. Let's find the derivative, dy dx, and then use that dy dx to find the tangent line at a given point. And so let's take the derivative, d dx of both sides of the equation equals d dx of 1. The derivative of x is just 2x plus the derivative of y squared, dang it, the derivative of y squared, if we treat that like x, would just be 2y, but then you need to multiply by dy dx because it's not x, it's dy, or it's y, and then this is equal to 0. And then now we solve for dy dx, so dy dx is equal to -2x and then over 2y, and so that's what dy dx is. Now find the equation of the tangent line at √2 over 2 comma √2 over 2. So that's dy dx evaluated when x comma y equals the following point, √2 over 2 comma √2 over 2. And so the reason why I want to do x comma y equals √2 over 2 is because this expression has an x and a y, and so we have to plug in both values. And so this is going to be -2, and then I plug in the x value, √2 over 2, over 2, and then I plug in the y value, √2 over 2, right? So I'm going to plug this value in for x right here, which gets plugged in right here. So that's where that comes from. And then this value right here gets plugged in for y, which is going to be that value right here. And if you simplify that, that just equals -1. And so the slope at that point is -1. So now we have a point. We have a point, which is the following, √2 over 2 comma √2 over 2. And we have a slope, right? The slope is the derivative, which we just calculated. It's -1. So it's -1. So the tangent line will be y minus the y value, √2 over 2, equals -1 times x minus the x value, √2 over 2. And what happens if we solve that? For y, we get y equals -x. And then this becomes positive from that. And then adding that will just give us actually plus √2. And so that is the equation of our tangent line. And so if we were to graph that, just a real quick sketch of what that graph would look like. So what it would look like is we'd have the unit circle. And then the idea is at that point, 45-degree angle, we'd have this tangent line right there. That would be the tangent line right there at the point √2 comma √2 over 2. And so it has slope -1 and it has that point, and this is the equation of that line. And the way we found it was using implicit differentiation. So that's a pretty simple one. Let's do some more complicated ones. Find y prime of x. And so this is, again, the same thing. This is the same thing as saying dy dx, by the way, if we have this function. And so we want to take d dx of both sides of sine of x, y equals d dx of x squared plus y. This one is actually quite complicated because we have an x times a y inside of a sine. And so we have to use the chain rule. So the derivative of the outside function, evaluated at the inside function, and then times, we have to take the derivative of the inside function, d dx of x times y, right? So this, where's this coming from? This little bit right here, that's chain rule. That's from the chain rule. And what's this equal to? Well, it's going to be equal to 2x plus the derivative of y with respect to x is just dy dx. So that's just dy dx. And now we just need to figure out what that is. What is the derivative with respect to x of x times y? Well, let's do it in a little aside over here. So d dx of x times y. Well, this is the product rule. So it will be the derivative of x, which is 1, times the regular of y, plus the regular of x times the derivative of y with respect to x. And this is by the product rule. So I don't need the box that big. This is by product rule. So that's how we'll get the derivative of x times y, and we'll plug that in. Plug this in right here. All right, maybe I'll even make that box green. So we're gonna plug that in right there. And so the final answer is we get that this is equal to cosine of x times y times, in parentheses, y plus x times dy dx. And then is equal to 2x plus dy dx. Whew, so that was a lot. But we're not quite done. We still need to solve for dy dx, right? We need to isolate dy dx. So we got to distribute. And so this is equal to y cosine of x times y plus x cosine of x times y, and then times dy dx. And then that's equal to 2x plus dy dx. And now what we do is we move this term over here, move that term over there to get the things with dy dx on one side and things that don't have dy dx on the other side. And so let's do 2x. I'll do it the other way, minus y cosine xy. It doesn't matter. So I'm going to subtract that guy over there and flip it. This is actually probably really the worst way to do it. Let me switch that back. Let's make that a minus and make that a plus. And then this would be dy dx minus x cosine xy dy dx, right? And so now I can pull a dy dx out of both terms and then divide. And so what do I get? The final answer will be dy dx equals, and then pulling it out, it's minus 2x plus y cosine of xy divided by, and then it's 1 minus x cosine xy. Whew, that was a doozy. So that one had a lot. It had a chain rule, it had product rule, it had some difficult algebra to solve for it. And so that's kind of the, then this one's honestly not even the hardest one. There are harder ones. And so just to kind of show you how this can get complicated really fast. All right, now let's do another example. Whoops, I forgot to delete this. Sorry, cut that out. I forgot to delete. Sorry about that. So finding tangent lines with implicit functions, find an equation line to the tangent to the curve at the point. And so we need point, which they give us is 3, 2, and slope, which is going to be the derivative with respect to y, or with respect to x, dy dx, evaluated at the point 3. So maybe I should say x comma y equals 3, 2. X comma y equals 3, 2, right? And so how can we do that? Well, let's find dy dx. So step one, find dy dx. So let's take the derivative with respect to x both sides. So d dx of x squared plus xy minus y cubed is equal to d dx of 7. Well, that's easy. That's just 0. And so this one is 2x plus, and we've already done this one using the product rule. Remember, it's 1 times y plus x times dy dx. And then minus 3y squared is how I take the derivative of that if it was just like taking the derivative with respect to y. But then I need to multiply by dy dx because it's not x, it's y. And then that's equal to 0. And then finally, not finally, but next step is to move the stuff with dy dx to one side and keep the other stuff on the other. So 2x plus y equals, but actually I'm going to do something clever here. Because actually I don't need the expression dy dx. I need dy dx evaluated when xy is equal to 3, 2. This expression right here has x, y, and dy dx. And so what I could really do is I could just plug in the numbers right now and then solve. So I want to find this actually when x, y, 3, 2. So that's not even step 1. So what we need to do is we need to find that. And so what we did is we took the derivative with respect to x on both sides, and now we can just plug in. And so maybe write this in red. So at this stage, plug in x comma y equals 3 comma 2, and then solve. The reason why we do that is because we don't actually need an expression for dy dx. We just need what dy dx is evaluated at a certain point, and it will save us a lot of time if we just plug in the numbers now. And so this is going to be 2 times 3 plus 1 times 2 plus 3 dy dx minus 3 2 squared dy dx equals 0. So that's how I get to that line. So that's how I go there. That's a horrible arrow. I could do better. That's better. And so what does this give us? This gives us 8 plus 3 dy dx, and then minus 12 dy dx equals 0. And so what does that give us? That's minus 9. And so dy dx is equal to 8 over 9, right? Because if you subtract 8 from both sides and then divide by -9, you're going to get 8/9. And so that is the slope. So this is our slope. That's our slope at the point 3, 2. And so now we have the point and the slope. And here's the picture of it. Let me move it over to the side. And so they gave away the answer, but let's just finish the work. So the point is y minus, because the point was 3, 2. So y minus 2 equals 8/9 times x minus 3. And then if you solve for all that, you get that y equals 8/9 x minus 2/3. And so that is the tangent line. And then this is kind of the picture of what's going on. This curve right here is kind of this cubic little curve. And then to find the slope of the tangent line right there, we solve for dy dx and then plugged in the point. And to get that's the slope. So that's our tangent line. All right, let's do, for sake of time, I'm going to skip this example because we don't have a ton of time. And so what I'm going to do is I'm going to skip to the next example. It's actually, that one's very, very similar to the last one we just did. So let me skip to this final example and then we'll end there. And then again, because this homework is a little bit harder, if you guys need me to do more examples, just let me know and I can make another video. Okay, so we want to find higher order derivatives. So remember how we defined d squared y dx squared is y double prime, and then d to the n, dx to the n, y is just y to the n, so that they're taking n derivatives. We can do implicit differentiation to find higher order derivatives as well. So if I'm given this implicit function, I could find the second order derivative for it. And so what do? I can take the derivative with respect to x on both sides. So that should seem very familiar because that's our first step always, is to take the derivative of both sides. And then I get 2x plus 2y dy dx equals 0. And now I can solve for dy dx. And what do I get? I get dy dx is equal to, if I do it, it will be negative x over y, right? Because the 2's will cancel. So negative x over y. And now if I want to get d squared y dx squared, I can just take the derivative again. So then take d dx of both sides again. And then what do I get? D dx of dy dx. That becomes the second derivative, right? That will become the second derivative. You can kind of think this as a dx times a dx, which is a dx squared, and a d times a d. That's where this notation comes from, by the way, d squared y dx squared. It's because the dx is squared and the d's get squared. And so this is equal to d dx of negative x over y. And so I have to take the derivative of that thing with respect to x, and just remembering that whenever you take the derivative with respect to y, or derivative of y, you have to multiply by dy dx. And so what does that give us? This is d squared y dx squared, because that's what the second derivative is. And then the derivative of this, we have to do the quotient rule. And so the quotient rule is low d high, so y times -1 minus high, negative x, d low, which is dy dx, all over low squared, which is y squared. And so now we have an expression of d squared y dx squared in terms of yx and dy dx, but we have dy dx in terms of x and y. And so let's plug that in for that right there. And now we'll have an expression involving only y's and x's. So this is negative y, and then it will be plus x times negative x over y divided by y squared. And that's honestly fine, but I want to simplify it a little bit more. Let's multiply top and bottom by y. So I get negative y squared, just to get rid of, I want to get rid of that y and that y. That's the reason I did that. So I get negative y squared, then it'll be minus x squared, and then all over y cubed. But then to actually do one more kind of crazy trick, so this is totally fine, but actually the fact that x squared plus y squared equals 1, I can use this fact all the way from up there and bring it all the way and plug it in right here, right? Because that's actually just negative x squared plus y squared. And so what is this actually going to equal? It's going to become -1 over y cubed. And so the second derivative, d squared y dx squared, the second derivative is really just -1 over y cubed, which is kind of crazy. So it only depends on the y value, how the second derivative is going. So that's kind of cool. And so that's implicit differentiation. Again, this homework is really hard, but I think it's good practice and it will make you stronger. So I'll see you guys. Take care.